think they were like.
I was in love with water and everything.
So we
What are
only
you
got
talking about?
another joke.
Alright.
Did you have to ride their bikes? Why? There's so many people.
Camping intense. What else did I- Intense. Oh, I get it now. Okay, we're still recording. I just wanted to make sure that it's still
I'm so
recording.
confused.
Okay.
Fancy. Tense, like.
Yeah, like the tents.
Yeah. Camping.
Alright, so I believe this is where we left off. Right. Test. Okay, it's a little better. Okay, so we were talking about how some diseases may result from the improper folding of proteins. How do proteins fold the way that they should? So I mentioned cystic fibrosis, Alzheimer's. So yeah. See, look at with my triple screens, that doesn't go dark either. Nice.
Wait.
I got triple screens.
Triple? You have 3?
1, 2,
Oh.
3. This is the tone screen.
What's that one for?
I'm gonna try when I Zoom with my students because it's just like too many windows. And then the formatting on my laptop just gets all big and 1995-ish. So yeah, it brings back horrible memories of dial-up. Okay, so here we go. So I think we were here. Denaturation inactivates proteins. Basically, it's when proteins unfold, and it could happen for several reasons. Number one, the environment changes. So either the pH becomes too acidic or too alkaline, the temperature increases or gets too cold, or maybe some type of ionic concentration messes up the folding, because ions have positive or maybe negative charges, and it could disrupt the tertiary structure of that protein, the hydrophobic inclusion, or the ionic bonds, hydrogen bonds, all of those. When proteins are denatured, they are inactive, so biologically inactive. They don't carry out their function or their job. They can be refolded and come back and become active again. So that's why we just call them biologically inactive. They're not dead per se, but they are inactive. They're not doing their job. So when we pickle items, like cucumbers to turn into pickles, or maybe beets or green beans or whatever you pickle, or even salt curing, what that is actually doing is just keeping microorganisms from growing or prolonging the life of food. So enzymes, or the proteins that are found in cells or in any environment, does have a limited range of physical parameters. So that's why if the pH changes, like outside its normal parameter, then it will denature and unfold and not work properly. So last year we did the liver lab, and I believe we changed the pH of it, right? We didn't look at temperature, or did we? No, I think we just looked at pH. And we kind of had mixed results. Some people, their highest was at pure water. Some people slightly basic, and that would make sense because our blood is slightly basic, and beef, they're similar to humans. Not saying that they are exactly like humans. So those that had slightly basic had the higher foam height versus the acidic, where it was just really, really tiny and small. So I used to do the liver lab, but we'd look at temperature. So you take your test tube holder and hold it in a hot water bath and basically cook the liver, and then have another slice and cold. But now that I have this cool macromolecule identify the mystery substance, we'll just keep that liver lab in sophomores. Right? Okay. So denaturation, like I said, it's inactive. So when the environment is reestablished, when it goes back to its normal parameters, it can refold. And so we just call this renaturation. So the fact that proteins can spontaneously renature means that the tertiary structure is influenced by the primary structure. So that's proteins in a nutshell, really. This is our last slide on proteins.
Is nucleic acid the big one? Oh, that seems like it. Yeah, is that one a big one?
So we are on slide 109 of 133. We'll be okay. But I think I have a lot of pictures. because I think the first section was just about carbon, and then the second section was carbs, then third was nucleic acids, and then fourth was protein, so then this should be fifth, right? Okay, let's do some review questions on proteins, several review questions. All right, here we go. So what chemical bond is responsible for linking amino acids together to form a protein? Peptide. Nice job. Peptide. Okay. This is carbs. That's pretty much found everywhere. And that is nucleic acid. What monomers make up a protein? C. Amino acids. Okay. This is nucleic acids. What's monosaccharides? Carbs. And then we're going to get to lipids here. Which part of an amino acid has the greatest influence on the overall structure of a protein? B. The R group. For an amino acid, they have the same NH2 amino group, the same carboxyl group, and it's not A or C. That's trying to trip you up. So it's B, the R group. A mutation that alters a single amino acid within a protein can alter. It is D. Yeah, come on in. Yeah.
There's not enough send out staff. So can you, like, I have a lot of, I've had some people pass on, I've got Thursday pretty good covered.
Yep. Okay. There were some parents that were asking if they could help, so
Okay.
I will ask and.
Okay, I'll send this out to staff so they know and stuff.
Yep.
Also, could you get me some things to send out to the ADs? Millbank's inquiring what time they gotta be here and all that.
Yeah, well, I was just going to ask you about that. Like, so Tri-State wants to go at 10 because I spoke with her last night,
Okay.
and I want to go at noon so I can clean up the course afterwards and do.
Yep.
So, like, should I put them at the 10 with Tri-State, and then I can have Lucas assist 10?
Whatever you want, that's fine.
Okay, then tell them 10, and I'll. I just got to change.
Okay.
I'll send it to you as soon as I
Well, no,
second
that's fine, that's fine.
Thank you. Yep.
Would they like color? Do you like to?
Okay. Sorry about that. Okay, so yes, it's D, all of the above, because when you change the single amino acid, obviously you're affecting that primary level, but then the primary level is like the base of everything. So very good to recognize that it affects all levels of protein structure. All right, which of these factors contributes? Oh, geez, Louise, get back. I got to change the sensitivity. I just found out that I can do that. All right. Which of these factors contributes to the diversity of protein form and function in the cell?
All of them. Is it all?
It's all of them. It's all of them, yes.
I feel like when it says all of the above, I just always forgot it.
Be careful on that with the exam, okay? Because, like, when you get to your exam, you won't have 4 options. Some of you usually have 5. And when I can't think of another option, I just say all of the above. And it's usually not it, so just be careful. Okay, so that was proteins. We talked about the levels of structure, motifs and domains. Remember, motifs are reoccurring themes, and we use them to figure out unknown proteins and what they might possibly do for us. And then the relationship between the 3D structure and basically its job. So moving on to lipids, hydrophobic molecules. We'll talk about the structure of triglycerides, how fats function as that energy storage molecule, and then how phospholipids play a very important role in the cell membrane and forming boundaries between the environment and the cell. So, lipids, section 3.5. Lipids have one main chemical characteristic, and that is they are insoluble in water. They do not dissolve, they hate water, they repel against water. Examples of lipids are fats, oils, and waxes. Another unique characteristic of our lipids is that they have this very, very high proportion of carbon and hydrogen bonds that form extremely long chains, as you can see in this faded background of this slide. So with these long chains, they can't fold up like a protein. Instead, they cluster or clump together, and they are usually trying to get away from polar molecules, usually.
why can't their chains pull down?
Why can't there what?
Their chains pull down?
Because it's literally too long. Like, I'll show you some 3D images of what they look like.
I like your background.
Thanks. I do too. It's one of my favorites. Although I probably should replace that, but, you know,
I can't even see what that is.
that's Duff beer. Alright. So, fats are very complex polymers, and their basic structure is you have a fatty acid attached to a glycerol group. So, these are the two types of molecules, the fatty acids and the glycerol group. Fatty acids are the long chains. They have a COOH at one end, and then they just have hydrocarbons extending from it. And then we have a glycerol, which is a 3-carbon polyalcohol. Basically, it has 3 OH groups. So another functional group here. This is also a functional group. So a lot of fats or lipids we come across, they have one glycerol, and then they have 3 fatty acids attached to it. And because of these 3 fatty acid chains that are attached to that one glycerol, we tend to call it a triglyceride. So 3, and then glycerol for the molecule glycerol, and then I gotta answer this. This is the porta potty guy. Brittany Erickson. Yes, it is. Yeah, I think I kind of figured out what we're going to do, so we're going to be okay. Sorry to waste your time. So, all right. Yep, thanks for calling back. Okay, bye.
You got your body situation?
Yep, we're going to go with the guy in Hoffman. Say what? I don't know, it's HPS. Hansen? No, not Hansen. Hansen? I don't know. Your sister referred him to me, so. And he's done business with the school before, so I was like, double bonus. Okay. So, glycerol and fatty acids. Moving on. I lost my mouse. So here's the structure of a fatty acid. The hydrocarbon chain with the carboxyl group on this end. This is showing a triglyceride, or the glycerol molecule, but when you stick it all together, here's that glycerol molecule and then the 3 fatty acids. So this is called a triglyceride. Okay, so because lipids have a lot of CH bonds, they can store energy for the long term. So fat stores energy for long term. There's actually 2 types of fats. Maybe you have come across these terms, saturated and unsaturated, and had no idea what they meant. Well, now we're going to find out what those 2 terms mean. So saturated means that of all the carbons that are listed, they are bound to hydrogen to the full extent. It has all the hydrogen atoms it can possibly hold. So if I just have 1 carbon molecule, how many bonds can carbon hold? Like how many bonds can carbon form? Sorry. How many bonds? 4. Okay, look at the periodic table. Carbon can form 4 bonds. So how many hydrogens can it hold? 4. Okay, so that would be a saturated molecule right there, because it can hold all of the hydrogens that it possibly can. Now, unsaturated means that we can't hold all the possible hydrogens. We have some double bonds occurring. So if I'm looking at, we'll just say a 2-chain lipid, even though those don't really exist. This would be saturated. because it's holding all possible hydrogens that it can hold. Okay, this would be an example of unsaturated. Now, carbon can only form 4 bonds. 1, 2, 3, 4. Here's this carbon. 1, 2, 3, 4. And then it's got hydrogens over here and over here, so everything's happy. So over here I had 6 hydrogens. That was the max. But over here I can only hold 4 hydrogens. So this is unsaturated. When you come across double bonds, now you have an unsaturated fatty acid or fat molecule. So what does this mean? Well, shape does affect its structure. Saturated fats tend to exist in solid form at room temperature, whereas unsaturated fats tend to be in liquid form at room temperature. So like a stick of butter usually stays in solid form at room temperature. It doesn't melt. You know, room temperature like 70 degrees Fahrenheit, it'll stay in a solid form. Olive oil, vegetable oil, those are unsaturated lipids because they exist at a liquid form at room temperature. So here's a saturated molecule. It's holding all possible hydrogens. And over here, now we have a double bond, and we're not holding all possible hydrogens that we can. Now, to mention, we've also got a little kink into it, right? This is a nice straight chain fatty acid, but double bonds tend to form kinks. So here's my saturated fatty acid. Over here, now because of these double bonds, the legs get all wonky. Okay, they're not nice and straight. They bend, right? So because they bend, you can't squeeze them together nicely because their legs are like knocking into each other, and that's why they exist at a liquid state. Whereas here with solid, we can arrange them very nicely and get that nice sturdy structure. Questions on unsaturated and saturated lipids? No, pretty cool, I think anyways. So, liquid fats, kinks. Solid fats, no kinks, straight leg. So I just said that the double bond changes the behavior of the molecule. It affects its melting point. So they have low melting points, thus at room temperature they are liquid state. Fats that are saturated, that's supposed to be that are saturated, wow. Solid at room temp. Okay. There are other kinds of lipids, not just fatty acids, okay? Terpenes. Terpenes are usually associated with pigments, so chlorophyll is a lipid. Retinol, which is found in your eye that helps you detect light, is a lipid. Natural rubber is a lipid. Okay, another example of a lipid, steroids. Steroids kind of have a unique shape, and I think I have it on the next slide, or 2 slides from now. Yeah, 2 slides from now. where they have these 4 carbon rings arranged in a certain way. And my college professor always mentioned it like a house with 3 garages. So I'll show you that. So some examples of steroids: testosterone, estrogen. These are natural steroids, but obviously you can take more steroids, and I'm sure you've read about that in the news with sports and all that. Prostaglandins here. These are basically hormones. Find them in a lot of vertebrate tissues. They just act like chemical messengers, turn things on and off. Okay.
What? The last 2 words?
Vertebrate tissues. Animals with backbones. So diagram showing some common terpenes that we may encounter in everyday life. The smell of pine, okay, pinene, cedar, rosemary, peppercorn, citrus. Hey, there's that lemon molecule we talked about, left versus right. Mints, lavender. So they're very aromatic. They smell. So yeah. Here's the steroids I was showing you about. So you notice we have like hexagon, 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 pentagon. So my professor said like a house, because we usually draw our house like a pentagon with 3 garages. So yeah. So if you ever come across that shape, that outline, it is a steroid. That is literally a common characteristic in all steroids. So here you can see that we have cholesterol. 3 houses, the house with the 3 garages, embedded in the phospholipids to help give it a little bit more structure for the membrane of a cell. So I think that's where I'm going to go now.
So the house with 3 garages is a steroid?
Yes. Yep, so cholesterol is, yeah. So cholesterol belongs to that category. All right, so fats, because they have all of these hydrocarbon bonds, they are an excellent energy storage molecule. When you compare the amount of calories, like a gram of fat versus a gram of carb, you get 9 kilocalories versus just 4. So we can store twice as much energy, basically. Now, animals, we can produce fats. Oh man, another typo. We tend to form them in the saturated format. Okay, all hydrogens, all carbons can carry as many hydrogens as they possibly can.
Is that supposed to say fats?
It's supposed to be fats, sorry. And the plant fats are unsaturated, so they exist as oil. However, they can be converted to saturated fats. So oil can be converted into a solid fat just by adding a hydrogen. Peanut butter, peanuts, that's a plant. They are artificially hydrogenated to form peanut butter. So they add the hydrogen to it, so peanut butter exists as a solid form. Now, if you buy like organic peanut butter, a lot of times when you open up the lid, you'll see like a thin layer of peanut oil at the top, and you just like stir that up. Well, that's because peanut butter is very oily. It's a plant. So now this can be pretty harmful to your health. It can produce a trans fatty acid. So I'm sure you've said, no trans fat, 0 trans fat on like chip bags and everything, right? Well, they're just saying that, we didn't add any hydrogen here to increase cholesterol in the blood. If there are trans fats, then you are increasing cholesterol in the blood, and margarine does the same thing. So. Okay. Last thing I want to talk about is how lipids play a very important role in cell membranes. So one type of lipid, phospholipids, form the cell membrane of cells. It is kind of a complex lipid molecule. It has 3 subunits. A glycerol group, just like it does in the fatty acid, triglyceride, with a hydroxyl group forms basically the backbone of it. Then we have 2 fatty acid chains attached to the glycerol backbone, and then a phosphate group on the outside of the glycerol. So we end up with a molecule that has both polar and nonpolar properties. The fatty acid tails tend to have nonpolar properties, and the heads of these phospholipids tend to be polar. So the tails, because they are nonpolar, we call them hydrophobic. They hate water, and if they are in the presence of water, they will fold in with themselves with other phospholipids to get away from that water. Where the heads, because they are polar, they tend to enjoy water, so we call them hydrophilic heads, and they interact with the water part, and it's mostly because of that phosphate group with that charge. So phospholipids made up of 3 parts: glycerol, fatty acid, and a phosphate group. Fatty acids give it its nonpolar hydrophobic properties. The phosphate gives it that polar hydrophilic property. Okay, so here's the diagram of a phospholipid. First a cartoon, then the molecular, then the 3D ball and 3D ball model. Ow, lost my mouse again. There it is. So here's that hydrophilic head made up of that phosphate group. This is the glycerol. It's kind of like the neck, so it attaches the phosphate to the fatty acid tails. Fatty acid tails are hydrophobic. So this is the polar region that hangs out with water, and these are the tails that hate water, so they'll hang out with tails of other other phospholipids. This is your last slide, just so you know, of notes. So the polar head, basically the phosphate, and then 2 nonpolar tails. Because it has a polar region and a nonpolar region, we call it amphipathic, because it kind of behaves like a polar molecule as well as a nonpolar molecule. It has that ability. It has that duality, I think is the word I wanted to say. So because it behaves, because it enjoys hanging out with water and also hates water, it's got a part that hates water, it's very essential in forming spheres. And we call these spheres micelles because the tails will face inward. And this is actually how detergent works to remove grease. Kind of forms like little vesicles around the dirt to lift it out of the clothing. Not only that, it forms a boundary, so chemical reactions can occur more efficiently. And it can also be selective as to what comes in and out of a cell, which we will focus more on in Chapter 4 when we talk about the cell and all the organelles and the common features of a cell. I'm trying to remember what Chapter 5 is about. I know 6 is metabolism. Of notes, yep, and then I have a diagram and then review questions. So this next slide is going to show how it can form a micelle, or a vesicle, or a sphere, basically, around something, because the tails will interact with each other and the heads will interact with the water. So here's my hydrophilic head, and here's my hydrophobic tails. And when you put it in the presence of water, it will hang out with other phospholipids, basically. So you see all the tails are interacted, and they're sheltering themselves from the water on the outside. And the heads love water, so they're interacting with that water. So over here, because of the two tails, we can form phospholipid layers. This is the cell membrane. So that's lipids. Sure. This one? This one. Okay. All right. So we talked about the structure of triglycerides, where it has a glycerol with 3 fatty acids. Their function as an energy storage because they hold so many carbon-hydrogen bonds, so they can carry twice the amount of energy versus a carb. And then how phospholipids play a very important role in the job of membranes because of those hydrophilic and hydrophobic interactions. So review question, what chemical property of lipids accounts for their insolubility in water?
Is it B?
It's B,
Yes.
a large number of nonpolar CH bonds. So, oops. The spontaneous formation of a lipid bilayer in an aqueous environment occurs because it's D. Yep. So I heard someone say A. Yep, that's true. And then I heard someone say C. Yep, that's true. So then D, both A and C. So, yeah. All right, we did it. Yay.